Okay, 4.6, we are looking at polynomial functions. And polynomial functions are just power functions where our exponent, that x is raised to, is a non-negative integer exponent. So over here are a bunch of power functions where that n is any real number. We have n being 0, x to the 0 power, x to the first power, x squared, x cubed. Here's x raised to a negative 1 or x raised to a fractional exponent. But with our polynomial functions, we're just looking at power functions where that n, that exponent, is a non-negative integer exponent. And that is basically the basic equation that is going to build all of our polynomial functions. So let's look at our idea of polynomial functions. So if you think back to Algebra 1, where we were first writing a polynomial function, we would always write our equations in descending order. We would take the term that had the highest exponent, and we would write that one first, and we would have them go down from largest exponent to smallest exponent. So this is just an example of how we would be writing from largest exponent to the smallest exponent. And keep in mind that the degree of our polynomial function, we would always look at whatever that largest exponent was, and that would tell us the degree of our polynomial equation, of our polynomial function. So on A, our degree is, the highest degree is the 3, the exponent of 3. So we know that this is a third degree polynomial function. On B, our highest exponent is the 7, that largest degree, that largest exponent. So this is a 7th degree polynomial function. We have a first degree because our exponent of 1, and on D, we have x raised to the 0, which means we're looking at a constant here, y equal to 7. Okay, and here are some examples over here on the right of some graphs of our polynomial functions. The red graph is just showing a 4th degree polynomial. We have a linear first degree straight line for the green graph. We also have another first degree here with our orange line, and the blue is a 2nd degree, or our parabola. So in terms of polynomial functions, some characteristics of them is your graph, when you're looking at a polynomial function, is always going to be continuous. There will be no breaks, there will be no cusps. So if we look over here at the left, these are not polynomial functions. This picture over here on the left has a break in the graph. Okay, polynomial functions cannot have a break. The second picture over here has a cusp. This sharp little point right here is what we refer to as a cusp. And so that also is not a polynomial function. So your graphs are always going to be this nice, smooth, continuous curve as you're seeing above. Second thing about polynomial functions is whatever the degree of the polynomial is, so if it is a 3rd degree, if it's a 7th degree, if it's a 9th degree, so whatever that largest exponent is that tells us the degree, then the number of turning points for your polynomial will be at most n minus 1. So if we have a 7th degree polynomial, then you will have at most 6 turning points. If you have a 5th degree polynomial, you would have at most 4 turning points. And if you think about x cubed, remember this curve looks like that polynomial, that's a 3rd degree. The number of turning points that x cubed has is 0 turning points. Okay, so it's at most. It doesn't mean it has to have that many, but that's the maximum number that it could have. On the third characteristic of our polynomial functions, as the absolute value of x gets large, the absolute value of y gets large. And what does that mean in English? Well, if we look at our polynomial equation here of x cubed minus 2x squared plus 3x plus 5. If I were just to factor out the x cubed, so write that equation in a factored form, I'd have x cubed times the quantity 1 minus 2 over x plus 3 over x squared plus 5 over x cubed. And if we consider the x value a very large value for x, then if I were to have 2 divided by a very large number, the larger that x gets, the smaller this fractional quantity is going to get, and that fractional quantity of 2 divided by a very large number is going to get closer and closer to 0. Likewise, if I take 3 divided by a very large number squared, 3 divided by a very large number squared also is going to get closer and closer to 0, the larger that x gets. And same idea with 5 divided by a very large number cubed. That quantity, as x is getting bigger and bigger, is going to get closer and closer to 0. So over a very large domain, as x gets very, very, very big, this whole quantity here is basically going to go out towards 0, and this x cubed is what is going to take over. So the highest degree is the overall idea of what that polynomial function is going to end up looking like. The rest of these terms basically become irrelevant over a very large domain as x gets very, very, very big. Okay? So if we keep that idea and we look at the general idea of f of x equaling x to the n, for all of our polynomial functions where n is an even number, if we look at this blue graph here of x squared, the pink graph of x to the 4th, if I were to graph x to the 6th or x to the 8th, basically I'm just looking at forms of x squared. It's just the larger that exponent becomes, the narrower that x squared, that U-shaped graph becomes. But the overall shape is always this parabolic x squared shape. Same idea for x raised to an odd power. If n is odd, whether we're looking at x cubed here in blue, x to the 5th, the one in pink, if I was looking at x to the 7th, if I was looking at x to the 9th, if n is an odd exponent, the same shape is still going to be this basic x cubed shape. Just the larger that number is, that odd value for n, the steeper, more narrower graph, but it is still that basic shape of x cubed. So basically all of your polynomial functions are going to take on a form of either x squared or x cubed, depending on if n is even or n is odd. Okay? Our n behavior. Well, if all of our graphs are basically looking like an x squared or an x cubed, for our even degree, a positive leading coefficient, meaning we're looking at a positive x squared, which we know our graph should be opening upwards. As x is going towards a positive infinity, our y values here are going up. They're going towards a positive infinity. And as our x values are going towards a negative infinity, our y values are still going up towards a positive infinity. Versus for our even degree, our x squared with a negative leading coefficient, meaning that our graph should be opening downward. As our x's are going towards a positive infinity, our y values are going towards a negative infinity. And as our x values are going towards a negative infinity, our y values are also going towards a negative infinity because both ends of our graph are going down. We can also look at our n behavior for our odd degree polynomial functions. So if we're looking at an odd degree with a positive leading coefficient, which would basically be the idea of a positive x cubed, which we know should look something along those lines. As our x's are going towards a positive infinity, then we know that our y values are also going towards a positive infinity. The end of our graph is going up. Versus as our x's are going towards a negative infinity, our y values are going towards a negative infinity. The end of our graph is going down as we are going towards the left. And our odd degree negative leading coefficient, meaning that we're basically looking at negative x cubed graphs, which we know would be a reflected x cubed graph. As our x's are going towards a positive infinity, our y values are going towards a negative infinity. Our graph is going down as x is getting bigger. Versus as x is getting smaller, as we're going towards a negative infinity, the end of our graph is going up towards a positive infinity. So by the general idea of our graph, whether it is a positive x squared or a negative x squared or a positive x cubed or a negative x cubed, we know what the ends of our graph are going to look like, the behavior of the ends of those graphs because of the general shape of x squared and x cubed, positive and negative x squareds and x cubes. Multiplicity. So just like the word, you can see multiple, okay, is just how many times the same zero, the same x-intercept, the same root occurs in the function. So if we're looking at the equation of f of x equaling x minus 2 cubed, this exponent of 3 tells us that that root occurs 3 times. There is a multiplicity of 3 at the x-intercept at the root of x equal to 2. So if your multiplicity, if that power is even, that root occurs twice, then basically our graph is going to be touching the x-axis, and you're going to end up getting that parabolic type shape around that particular root because that's what the x squared graph looks like. Versus if you have a multiplicity of 3, something odd, 3, a 5, a 7. In this particular case, around the root of x equal to a negative 2 with multiplicity of 3, we're going to get this odd shape. It's going to cross through because we're going to get this x cube type shape at that particular root. So it's going to cross the x-axis. Versus our evens, it kind of touches or bounces off because you have that parabolic type shape around that particular root. So over here at behavior near our roots, what is going on as we get closer and closer to that particular x-intercept? What is the behavior of our graph? What is going on? So if we look at this equation of f of x equaling x minus 2 cubed times x plus 3 squared, we have two x-intercepts. We have an x-intercept at x equal to 2, and we have an x-intercept at x equal to a negative 3. And if we want to know what the behavior of our graph, what's going on with our graph as we get really close to this x equal to 2 and as we get really close to this x equal to a negative 3. So how you determine the behavior is the root where that x-intercept came from. So for x equal to 2, that came from the factor of x minus 2 cubed. So we're going to leave that factor alone. We're not going to touch it. And we're going to take the other factor, in this case the x plus 3 squared, and we're going to replace x with the 2. As we're getting closer and closer to x equal to 2, the values of x are getting closer to 2, and that's why we're substituting that value of 2 in for all the other x's except for where it came from. And that is where we get this 25 from. 2 plus 3 is 5, 5 squared is 25. So the behavior as we are approaching x equal to 2 here is going to look very similar to the graph of 25 times x minus 2 cubed. It's going to look very similar to this positive x cubed type shape. And if you look at your graph, you do kind of have this positive x cubed shape as we are close to the value of x equal to 2. Versus the behavior as we approach x equal to a negative 3, the negative 3 came from this factor of x plus 3 squared. So we're not going to touch that factor. We're going to leave that factor alone, and we're going to take that value of a -3, and we're going to plug it into any other x except for where it came from. So if I plug the -3 into this factor where it did not come from, a -3 minus 2 cubed, that's where this -125 is coming from. So the behavior as we're approaching this x-intercept of a -3 is going to look very similar to the graph of a -125 x plus 3 squared. Or it's going to look very similar to a negative x squared graph. And if we look at our picture here, we have this negative or reflected x squared type shape. And then we also could have just quickly found our y-intercept at a -72. And if we connect all of these behaviors together, that is where you're getting this red curve or this graph of f of x equaling x minus 2 cubed times x plus 3 squared. Okay. So in terms of steps for graphing our polynomial functions, first thing you want to do is try to figure out what that end behavior is going to be. Are you looking at a positive or negative x squared graph? Are you looking at a positive or negative x cubed graph? Is it going to be an x to an even, or is it going to be an x to the odd? Okay. Next thing you should be doing is looking and finding your x-intercepts. What are those roots? And what is the multiplicity? What are those roots? What are the powers that are attached to each of those roots? Are they even powers, so that around that root it's going to look like an x squared? Or are they odd powers, so around that root it's going to look like an x cubed? And figuring out that root behavior. Like I just said, the positive x squareds or the negative x cubes. And then lastly, if you have a y-intercept, quickly find that y-intercept. And if you put all of that information together, you should be able to very quickly sketch your graph. So let's look at an example. So on number 1 here, we have a polynomial function. All of our exponents are non-negative integer exponents. We can see that our largest exponent is the 3. So this is a 3rd degree polynomial, which means that our overall behavior of our polynomial should look like an x cubed graph, and particularly a positive x cubed graph, because our leading coefficient has a positive 1 coefficient, a positive there. So our behavior, or the end behavior of our graph, we know that a positive x cubed looks something like that. So as we go off towards a positive infinity, our graph should be going up. And as we're going towards a negative infinity, our graph should be going down. We want to find our x-intercepts, which means we're going to have to factor. We have 4 terms, so that means we need to factor by grouping. So I'm going to group first 2 and last 2. So with the first 2, I can factor out an x squared. I have my x plus 3. Last 2, I'm going to factor out a -4. I get another factor of x plus 3. We know with grouping, minimally we have to go 2 lines. This first line will always be a sum or a difference. With here now, we have a common factor of the x plus 3 that we can pull out. We're left with an x squared minus 4. And then I'm going to still factor those down. X squared minus 4 to an x plus 2 and an x minus 2. So there's the same equation, it's just now in a factored form. But in that factored form, I can see what my x-intercepts are. I have 3 roots, 3 x-intercepts. I have 1 at x equal to a -3, 1 at x equal to a -2, and 1 at x equal to a positive 2. And I'm just going to kind of come over here to sketch my graph real quick. So 1, 2, 3, 4, 1, 2, 3, 4. So I have an x-intercept at a -3. I have an x-intercept at a -2, and I have an x-intercept at a positive 2. We already said that it's a 3rd degree, So as we're going towards a positive infinity, we know that our graph should be coming up as x is going towards a positive infinity. And as x is going towards a negative infinity, we know that the endpoints of our graph should be going down, because that is what a positive x cubed looks like. If we look at our factors, our roots, where our roots came, our x plus 3, multiplicity of 1, our x plus 2, multiplicity of 1, our x minus 2, multiplicity of 1, which means it should be linear around each of those factors because of those exponents of 1. If we look at the actual behavior, if we look at the behavior as we are approaching x equal to a negative 3, that came from the factor of x plus 3. So I'm going to leave that factor alone, and I'm going to take a negative 3 and I'm going to plug it into the other two factors. So I'm going to have a negative 3 plus 2 and a negative 3 minus 2. And so in terms of my behavior, this is a negative 1, this is a negative 5, and so I'm going to get a positive 5 times x plus 3. Which we know that that is a positive slope line. And so our graph should be looking something like that. So around x equal to negative 3, we should have this positive slope line behavior. As we approach x equal to a negative 2, well, x equal to a negative 2 came from the factor of x plus 2. So I'm going to leave that factor alone. I'm going to plug a negative 2 into the other two x's where it did not come from. So I have a negative 2 plus 3, and I have this negative 2 minus 2. Here I get a 1, here I get a negative 4, and 1 times a negative 4, I get a negative 4 times x plus 2. Which that is just an equation of a line, a negative slope line, and we know negative slope lines should look something like that, slanting down from left to right. So as we approach a negative 2, we should have this negative slope line behavior. And our last root of x equal to 2, which came from the factor of x minus 2, so I'm going to leave that root alone. I'm going to take a 2 and I'm going to plug it into the other two factors where it did not come from. So I have a 2 plus 3 and a 2 plus 2. So this is a 5, this is a 4. So I get a 20 times the factor of x minus 2, which again is just a positive slope line, which means if we were to graph, it would be going up from left to right. So as we approach 2, we should have this positive slope line behavior. And if we go through and we connect all of those behaviors together, we said our end behavior, it should be coming down. We come up linear. There's got to be some sort of turning point so that it comes back down through the negative 2. There's a y-intercept that I actually did not solve for yet. Sorry about that. A y-intercept at a negative 12 and coming back up through the positive 2, and we know it's got to be coming up overall. And there is our graph of f of x.